So here's the URL, begin lesson. Actually, you can just go retake the quiz.
Oh.
Okay, so the quiz.
Wait, where is it that in the page?
Well, let's write it like this. Even if you go begin lesson, it says quiz.
Oh, okay.
And it should take you this, right?
Okay. We'll try that later.
Okay, get that to me today, guys, okay? All right, any questions over what we did the other day? Any questions on the lab?
Do you have any questions?
There were some. I think there was one or two questions that I had trouble understanding.
On the climate lab?
Yeah, the climate lab.
Okay, so what we're gonna do here today is we're gonna go finish the 2 labs. Okay, that'll be our goal for today. So the first thing is intro. Oh, I can't. Is Blackboard still down?
Yeah, it's been down for the last 2 hours.
Yeah, that's okay. So that's bad, just so you know. Well, I've got a copy of it. So let's go to the Earth-Sun relationships lab so we can finish that up. So all of this stuff, now this is your basic weather processes, right? And then it says which areas receive an excess of radiation and which act in a deficit. So if I do that, did you find, the answer should have been in the lab, but if I go Earth radiation deficit by latitude, you should be able to find an image that looks like this.
Yep.
And this one might be good. I mean, there's a lot. You see how they're all kind of different? But I kind of like, this one seems to be pretty decent. I'll use this one. Okay, general circulation of the atmosphere. So what are we saying? What latitude is this? Did anybody find the actual latitude? I think it's at 43 degrees. So if I use this, I guess I could do something like this. Or 38 or 39 degrees. I guess, does it really matter? Does it say so in the book, Lena?
I don't remember seeing it, but I could look again.
Because I noticed that they're all kind of different, right? They're all a little bit different. So it depends. It looks like around 39 degrees latitude. I wonder if we could go to, there's a lot of stuff on the internet. Have you noticed that? What is this graph that I'm showing you? What is this?
Could you make it bigger?
This graph. You know what this graph is. What is that?
Is that one the Boltzmann or is that the Planck's?
That's the graph is Planck's black body distribution.
Yeah, that's what it is.
But so this is the sun, this is the earth, and it's showing wavelength. Notice too that it's not a linear scale, it's logarithmic. The sun is to the left at 0.5, the earth is to the right at 10, right? But that's showing you more Wien's displacement law, because Stefan Boltzmann law would tell me what? What does Stefan Boltzmann's law tell me?
Is it the absolute temperature of a black body?
Well, what about it?
The total irradiance.
Right. And so what's that? What represents the total irradiance?
Was it the energy flux?
What represents the total amount of that? Shannon, what do you say?
I'm having a brain fart. Hold on.
Is it possible that you could unplug your mic and plug it back in? See if that works. You plugging it back in?
Can you hear me?
Yeah, well, when you talk, that's fine. But when you're not talking, go ahead and mute it. And the only reason, it's a really high whistle, right? Everybody else hears that, right?
Mm-hmm.
Yeah.
Yeah. Well, there's construction across the street from me, so I don't know if that's like
It doesn't-
making it
doesn't
weird.
sound like it. I don't think so, unless they're screaming or something. But what is this? What's the answer to my question? Isaac?
Is it E star?
What about it?
It equals iridescence, irradiance.
What does it equal?
It's sigma multiplied by temperature to the fourth degree.
Okay. But what does that tell me? How is this related to this graph?
Because that E star, the irradiance, is the intensity.
Well, yes, but how is that related to the graph? Now, this is where you guys are not getting this stuff. What is this called? This law.
Stefan Boltzmann's law.
Right? What is that law?
Wien's displacement.
What I'm worried about, guys, is that you're not learning this stuff well enough while we're learning it. And now in a week and a half, when we get back from spring break, you're going to forget even more. So you should be worried about your grade to the point where it causes you to act on that. Okay. How is Wien's displacement law demonstrated with this graph? Ryan?
So we would see the max wavelength at like the height, or I don't really know.
Well, don't let him sit there by himself talking or not talking. Help him out. All right, then talk to me about what you don't know.
I have a guess. Does it show, because irradiance is the flux of radiant energy per unit area, so does that have anything to do with like the question that we asked with, can an infinite perimeter circumscribe a finite area? Does that have anything to do with like the area in the graph?
Yeah, you're giving me, so what you're doing is you're giving me stuff, but you're not making sense of the stuff. You don't have any conversational skills to talk to me about this.
Okay.
Not you, Lena, but
Yeah.
all of you guys in general. You're missing the point, right? Knowledge and education is not about facts. Knowledge and education is about learning ideas, right? Your entire life, and this is why I think schools suck, and I think they're getting suckier, is you take tests that question things, facts, boom, boom, this. You have no idea what this means. Meaning is what education is. So I'm showing you this graph, right? And this graph, Lena said, is the Planck's black body graph. That's what this is. So it says intensity, but what is it really?
Is it temperature?
Ah. What should this graph be labeled?
Oh, irradiance?
Okay, it should be labeled E star, which stands for irradiance. Now, what is irradiance? Well, Ryan, you're on a roll. What's irradiance?
What is it? Like the amount of radiation per unit of area?
Yes. Give me better explanation of it. More informal.
Like from the sun, like, I don't know, every square mile or something, the amount of radiation given off from that would be the irradiance.
Okay, that's a more appropriate answer for an introduction to meteorology class, right? You think that you have to speak in like fancy language. I'm asking you not to speak in fancy language. You know who uses fancy language? People who really get something and then want to make it really succinct and clear. That's why we use fancy language. So do you remember when we drew the picture of the little tile of radiation coming out of it? That's irradiance. It's a what? What's the fancy name for irradiance? What's the fancy name? And I gave you the fancy name.
Intensity?
Not intensity. That's what this graph says. I don't know why that graph is that. I don't think so. What was the word I gave you for what E star irradiance meant? It's two words.
Is it energy flux?
It's an energy flux. And what is flux?
Isn't it a rate?
It's a energy what? What's a better word than flux, or a simpler word than flux?
Transfer?
Well, maybe transfer, but we say this about heat, even though it's not true. It's an energy what?
Change?
Not change.
Whoa.
What do fluids do, right, Isaac? It's an energy flow, right? So we're giving this idea to you that energy flows. And when I think about flow, right, it's not like it's a liquid. Do you understand that liquids flow or fluids flow? This is energy flow. So really what it is, it's energy passing through something. So in this case, we mean flow as an energy passing through. And it's passing through the outer edge of the sun, and then it goes traveling through space at the speed of light. So it's the energy flow. That's really what irradiance is. But the amount of that is what? What can you tell me about the amount of energy flow? What do you say?
It depends on the temperature.
Okay, use a little bit more sophisticated word than it depends on the temperature, even though that's a good start.
It is directly proportional to the temperature.
Way better word, right? That's a word that we should know now because you are more elegant or eloquent. You can speak better. It's so the energy emitted that flows out of the sun or an object is directly proportional to what?
Temperature.
But it's not just temperature according to that equation.
And the constant.
Now, it's not proportional to a
constant.
that just makes it work. It's proportional to a variable. And what's that variable? Well, you said temperature, but it's not just temperature. It's what? Look at the equation. Is it just temperature?
Temperature to the fourth power.
Okay, so it's temperature to the fourth power, but it's not just temperature. We call it something else. What's the word we would use before it?
Absolute.
It's the absolute temperature. In other words, we want to use a Kelvin scale as opposed to centigrade or Fahrenheit or whatever, right? We want to use the absolute temperature. So think about what you're saying. E star equals sigma to the fourth. Well, what that really means is the rate of energy flow via radiation through some area is directly proportional to the absolute temperature to the fourth power. Now I have said an intelligent sentence that is completely clear. Say it, Vina.
So what you said is energy flow is directly proportional to at the absolute temperature and to the fourth power.
Okay, now it's not just the energy flow, isn't it the amount of energy flow?
Oh, yeah.
Because we're talking quantities. So it's the amount of energy flow. How quickly energy, and think about it, what's the unit of irradiance?
Wasn't it a watt?
Not just watt,
Oh, watt times meter squared.
not times.
Oh.
I mean, if you look at it, it's this. It's times meters to the minus. So how do I say this?
Watts per meter squared.
Watts per meter squared, right? This means per, means through. And meter squared, right? When Ryan said energy flux, what did he use? When you said on the sun, he's like, there's energy flowing through like some what? You said square mile, if you remember. Which, it works. You could use miles. That's an area, isn't it? Square miles. But the proper one, the appropriate one is per meter squared. Okay, now, what's a watt? You remember what a watt was, Isaac?
Wasn't it a joule divided by a second?
So joules,
Mhm.
what's the word?
Per second.
So when you have it per second or per time, what are you making it? When you
a
take
rate.
something like a joule, which is a unit of energy, but you divide it by time, what are you making it, Zach?
You're making a ratio or a comparison.
No. If it's something per time makes it a what? It's like a ratio, but it's different.
Is a fraction or comparison?
Starts with an RAT. Isn't that a rate? So in other words, Lena, you could say it's the amount of you could say it's the energy is directly proportional to the average temperature to the fourth or absolute temperature to the fourth. But you really are saying the rate at which energy flows through an area
Okay.
is directly proportional to the absolute temperature to the fourth power. Now, hotter objects, because they're hotter, are going to give off more energy. So do you agree the sun's hotter than the earth?
Mm-hmm.
How much hotter?
Twenty times.
20. So how much more energy does it, at what rate does energy come out of the sun per square meter compared to that of the earth? It's
So
20 times hotter.
16,000.
No, a little bit bigger. 160,000.
Oh yeah.
20 to the fourth power.
Oh,
160,000. Okay. But now you still didn't answer my question. And my question is, how does this graph show me Stefan Boltzmann's law? What is showing me this? Aaron, do you know?
She's saying something. Comparing what?
Right, comparing what? How does this show me? Think about what I'm asking you guys. I'm using the word show. If you go to a show, what are you listening to something? I'm going to a show. I said, show me. Isn't that a picture? Isn't that something visual? What visually shows me the rate at which an energy flows?
She's saying comparing the wavelength to temperature.
Not wavelength, that's lambda max. That's this thing. That?
Yeah, I mean, you were asking about like what visually on the graph, like
Area. This is shown by looking at the area under the curve. Now, Lena, now we said the perimeter goes on forever, but the area is finite. Well, that area represents the amount of energy, or at least the total rate of energy flow from a black body. And we already said that the sun, we already said that the sun flows at 160,000 times more than the earth. Does that look like this area is 160,000 times bigger than this? Is this graph showing me this? Does it look like it's showing you that? Why not? What is this graph? What have I done to this graph? And I gave you this word, you just don't understand it yet. What word did you write down when I gave you this information the first time?
Was it either asymptotic?
Asymptotic means it's going to get closer and closer. It never really touches. It's not asymptotic. Do you guys have it written down, right? Zach, do you have it? And why don't we ever get to see your face? I like seeing your face.
Me?
You have a nice face.
Oh, my camera is like, it has a really short cord, so it can only go like a certain amount. I mean,
Oh, there you go. Now I see some eyes. That's at least more of a face. I was talking to my brother. My brother retired from Glenbrook South High School, and he does choir. And he was asked to sub long-term for somebody who was at a family leave or something. And so he's been going to classes, and he started giving Fs to students who didn't have their camera turned on. He gave them an F. Guess what the parents did? They responded. They were all angry. And he says, look, this is the deal. The students turn on their camera because I said so. And if they're getting an F, which means they didn't turn in work, you know why? Because they think they can get away with it, but they can't. So there you go. I come from a family of teachers. We talk about teaching a lot. Okay. What's the word that goes with the area? See, do you agree this area should be 160,000 times more than the Earth? But the graph looks like they're the same because this graph is what? Did you
Logarithmic?
The logarithmic, actually, based on the fact that it's logarithmic, would probably change it even more. It is logarithmic, but that's not what it's referring to. There's a word that I use for this. Starts with an N. Yeah. Maybe you didn't write it down. Normalized? Right? But does anybody have that in the notes? Isaac, did you see that or no?
No,
Do you remember talking about it?
I don't think I remember ever talking about this.
I mean, that's probably true, right? That's why we write stuff down, is to not to forget what it is. But then if I write it down, if I write something down, is it good enough just to write it down? You need to do something with it so that you do know it and remember it. Because remembering is part of learning, knowing it's way more. And the most important thing is being able to use it in a conversation. So normalize says we're just basically making it the same. I'm not worried about the area. They look the same to me because it's still a Planck's black body curve. So what is it that they're actually telling you in here? Well, let's take a look. All matter in the universe that has a temperature above absolute zero radiates energy across a range of wavelengths in the electromagnetic spectrum. What kind of wavelengths do all objects, especially black bodies, radiate? What kind? How long is this range of wavelengths?
Infinite?
It's infinitely long, right? So all kinds. That's what it says in the definition of black body. But do you agree that the further you are toward the right or the left, the smaller, the less and less it's giving off? The area underneath that curve gets smaller and smaller and smaller. So in reality, it's probably not giving a lot. But technically, according to the definition, it does. The hotter something is, the shorter its peak wavelength of radiated energy. What did we call this sentence here? The shorter the peak, what do we call the peak wavelength of radiated energy? Isaac. Just look at the sentence here for a second. Do you understand what it's saying? Because maybe you don't, and that's okay too, but I need to know this. Do you understand this sentence, or does it not make sense to you? Because maybe it doesn't.
Yeah, it makes sense.
Make it easier. Like, again, let's go back to the simple now. Make a simpler statement than this one. What do you think, my friend? Like, I want to help you and I can't read your mind. So you're going to have to say something, have a conversation with me.
I don't know what to say.
Well, what do you think it means? I mean, be wrong. I'd rather you be wrong. And then at least I know how you're thinking. See what I'm saying? It's a conversation because it's a hard concept. I'm not denying that it's challenging. I just don't know what you think about it.
Well, the temperature is related to the peak wavelength of radiated energy.
What do I mean by the peak wavelength?
The what's the word? Is that the crest of the wavelength?
Yeah, the ridge or something. What do you mean by? Are you talking about something like this?
Yeah.
Okay, no, that would not be right. But if that's what you're thinking, then I get that. So, Shannon, what do you think? What does this mean?
The peak wavelength, doesn't that mean like it's the total irradiated energy through the energy flux?
No, not that one. See, we didn't use the term peak wavelength. What did we use? We know what do we use?
Yeah, lambda max.
We use lambda max. Peak wavelength of radiated energy is what we call lambda max. So Ryan, does that, if I said this, the shorter it's lambda max, the hotter something is, the shorter it's lambda max. Does that make sense to you? And again, it doesn't have to make sense. I want it to make sense. So that's why I'm a teacher. What do you think? What do you see on that?
So, sorry, what are you asking for?
Well, I'm saying I have a sentence here and we didn't understand what it meant. It seems like it's an important sentence, doesn't it?
Yeah.
The hotter something is, the shorter, but and we didn't know what it meant by the peak wavelength, and so you got hung up on that. And I said, well, I called it lambda max.
So that's going to be what, velocity over frequency,
No,
maybe?
no, this
What
is not okay. The
Or
wavelength,
it's C over frequency?
the wavelength of any radiation is C over F, but that's the actual wavelength. That's the length of a wave. That's lambda. And it's inversely proportional. I get that, right? But that's not, lambda is not what lambda max is. So it makes sense of that. Zach, you try it.
Well, wouldn't it be like C over T, but C is always 2,898? Like, is that what lambda max is equal
Yes,
to?
it is. But what is that you just quoted us?
That's the Wien's displacement law.
Okay. So you just quoted us the law. Okay, fine. Say this in English. Say that in English for me.
could I say like lambda max is inversely proportional to the absolute temperature as long as C is equal to 2,898.
And since I just put the number in there at 2898, it's always 2898. That's always true. It's a true constant. So lambda max is inversely proportional to what did you say?
The absolute temperature.
Oh, he used the absolute temperature. Notice there's no fourth power. So what does that mean? Lambda max is inversely proportional to the absolute temperature. First of all, you still need to tell me what lambda max is. What do you think that means?
It's the point in which the we get the most energy flow out of an area.
Isaac, did you understand what Zach said?
I was writing down some things that are on the screen when he was saying that.
Okay, well then ask him again.
Could you repeat that, please? Zach?
Yeah, so I said lambda max is the point in which the energy flow is the highest for the given area.
Do you know what that means? Yeah, that was neat. Isaac, that's a really easy question. Did you understand what that meant?
I honestly, I don't remember a single thing that he just said. Even I'm paying attention right now. I'm just struggling.
Listen, it's not, this is not about you, really. It's not. Zach, just so you know what you just said, I would say I don't understand what you said.
Okay.
So did you understand that? No, I didn't understand that. You didn't remember what he said. So I would say to Zach, I would go, Zach, wait, I didn't understand what you said. And then you would say the same, use the same words. Zach, can you do that? Use the exact same words?
That I just used.
Yep.
So I said lambda max is the point in which we find the most amount of energy.
It's the point.
Or
I don't know what that means. I've had it. I'm at a point of no return. I'm at the point where I'm going to lose my temperature. This is a point. I'm pointing. There's a lot of uses of the word point. So I don't know what you mean by that. This is what I mean by explaining under concepts. I don't know what you said by the point. I've decided I want you guys to be skillful. I seriously, I want you to be smart people. I don't know if you've heard my exasperation with the world, thinking everyone's stupid, and I actually believe that. And we're getting stupider. So I'm trying to fight that by, use 6. So I'm going to make sure that doesn't happen. So I want you to understand this, and I want you to understand how to talk to some other human being, which this Zoom is not doing a good job. So we're losing our ability to even understand humans anymore. We can't talk to each other anymore. We're faces bobbing around on some stupid frame with high screeching whistles in the background. I'm thinking, we're human beings. We're supposed to relate. So I just want to talk. Isaac, more than anything, I just want you to understand this. Really understand it, not just, oh, I can pass a test. I want you to understand it. That would make me so happy. So Zach, and you're good, right? I know you got some thoughts there, but you just said it's the point where. I don't know what that word means. The point, what does that mean?
well, I was just going to express that where I was going to say it's like on the leg wave.
On the what?
So if we look at like the graph itself for the wavelength, if we
This-
look where the highest peak is for the sun and we go straight down to wavelength, that's the point I'm talking about.
Okay, so you're saying this. Is that what you're saying, my friend?
Yeah, so like that lake wave, like
So
where
this
that, yeah,
point, the top of this And what is this? What's the word for this? This is not a wave, right? The wavelengths of the various sizes of wavelengths is what's plotted here. But what is this thing? How would you describe what this blue line is? Like, again, in words.
It's the maximum possible emission for that wavelength.
For which wavelength?
So that line is just a series of ordered points.
Okay.
And so if we
So-
take any wavelength underneath that line represents the max amount of.
Well, I wouldn't say the max amount. It says how much is coming out, how much power is being emitted with that wavelength. Does that make sense? So I like the way you started, Zach. You're like, okay, this is just, so this, at any wavelength, that's what he said, right? At any wavelength, so I can pick any wavelength, I'll pick that one. This is a set of ordered pairs, which says at that wavelength, that's the E star, that's the irradiance, that's how much is coming out at that wavelength. Does that make sense? And then, do you agree that there's one wavelength that puts out more radiation than anything else? This is the amount, that's this point right there. That point is the top of this graph, right? This is the graph that I'm talking about. But does that make sense to you, first of all? Is that good? What is this graph called? What is this thing? It's not a wavelength. It's just it's a picture. But what do we call it? There's two words that I use for that. I could call it a curve. Do you agree it's a curve? I mean, if I said, look at this curve, you go, oh, that makes sense. I see the curve. But the curve, there's a special name for this because it's this wavelength gives off this much, this wavelength gives off this much, this wavelength gives off the most, this wavelength gives off some other amount. That's a what? This much at that wavelength. This much at that wavelength is a what? Starts with the D.
What
What's
is
the
the
next?
distribution?
It's a distribution. This is Planck's blackbody distribution, or Planck's blackbody curve. Those are words. It's a graph. But it's distributing energy at a wavelength. Now, do you agree that there's some wavelength that's more than any other wavelength? And that is at, like, and I like the way Zach said it, that is right there at the top of the curve. This point represents a wavelength, and that wavelength is lambda max. And lambda max, we said, the value of it is 2898 divided by the absolute temperature. So where this is inversely proportional to the temperature. In other words, if it's hotter, this lambda max should be what? Isaac? If the temperature of whatever object is giving off wavelengths is hotter, what should the value of lambda max be? Aaron?
She says cooler.
Well, no, not cooler. This is not a temperature. That's a wavelength. It should be what?
Wouldn't it be shorter?
It should be a smaller value, which, because it's a length, smaller lengths we call shorter. That's the words that we use. Which way is shorter on this graph? Isn't shorter that way. To the left is shorter. So let's do this again. I have the Earth and I have the sun. The sun is warmer. How do I know the sun is warmer from this graph? Because its lambda max is further left, shorter wavelengths. The hotter something is, the shorter its lambda max is. That's what the graph says. The hottest objects in the universe radiate very short wavelengths, like gamma rays and X-rays. Cooler objects emit mostly longer wave radiation, including visible light. Well, the sun is giving off visible light. This area in here, we said it's about 43% visible. Remember we used those terms? Thermal, infrared, radio, and microwaves. That means we're going further and further to the right, because to the right is longer wavelengths. So now here, guys, now does this paragraph make more sense? Well, you understand what you've experienced is called learning. What am I trying to test you on? How much you learned. Up until now, and this was a review today, you didn't know this, which says you're not learning, which means if I'm evaluating you by giving you a grade, what grade are you deserving based on the amount that you actually know? It would have been low. So do you see how we get to this place? We just take it apart a little bit at a time, and we either break it down into something simple, or we ask questions about what that really means. Because if you don't know something, then you don't know something. You can't learn something you don't know. Does that make sense to you? I mean, think about how much better you feel, Isaac, right? So that location is lambda max, which is 2898 divided by temperature in micrometers, and that's called Venus displacement law. Right? And it says lambda max is inversely proportional to the average temperature. Hotter objects radiate shorter wavelengths. Then we said the amount, E star, the irradiance, the watts per meter squared, the amount of energy flowing through an area in radiation is directly proportional to the absolute temperature of the fourth power. Hotter objects radiate more energy. Does it just twice as much more? No, to the fourth power times more. The sun is 20 times warmer. It gives off 160,000 times more energy. That's Stefan Boltzmann's law. That Stefan Boltzmann law on Planck's blackbody distribution is related to the area underneath the curve. Because this area should be 160,000 times that of this, well, that's hard to draw. Do you understand? If I drew it, it would be like this. That's not going to help me. So what I do is I make it so it looks the same, and I normalize it. Because I can, at least in the normal curve, in these normal curves, I can get the relationship of the wavelength, the lambda max, but the area doesn't look like this. Now let's take a look at this. Go ahead and read this out loud, would you, Ryan?
The surface of the sun has a temperature of about 5,800 Kelvin, about 5,500 degrees Celsius, or 10,000 degrees Fahrenheit. At that temperature, most of the energy the sun radiates is visible in near infrared light. At Earth's average distance from the sun, about 150 million kilometers.
Which
The
is
average,
miles. How many miles? How many miles is the sun on average? Remember the number? Aaron, you know what it is offhand?
93 million.
93 million miles, right? Go ahead, keep going.
the average intensity of solar energy reaching the top of the atmosphere directly facing the sun is about 1,360 watts per square meter. According to measurements made by the most recent NASA satellite missions.
Okay, hold on a second. So this is how much is hitting the, what? What's it hitting? Notice what it says. Remember I gave you this the other day? And that's because here's the sun. The sun is really big, and the Earth is over here really small. And the radiation is going out from the sun equally in all directions. What's the word? Equally in all directions.
Isotropically.
Isotropically. So that by the time it gets to the Earth, it's going to be this really huge circle. And then lots of sun energy coming from it. But by the time it gets to the Earth, this energy is less and less intense because it's 93 million miles away. And if I actually put a number, watts, how big is a light bulb? This is a 60 watt light bulb. The sun is a 1,360 watt light bulb per meter squared. That's a lot. Watts per meter squared. That's the irradiance hitting the Earth. Okay. One more sentence.
This amount of power is known as the total solar irradiance. Before scientists discovered that it varies by a small amount during the sunspot cycle, total solar irradiance was sometimes called the solar constant.
Oh, so we thought this was a constant, but because the sun gives off sunspots, sunspots is an active sun when there's a lot of sunspots, that means it's giving off more radiation. If it's not giving off sunspots, it's cooler. Do you think that impacts the weather? Seems reasonable. Let me show you something interesting here. Let's see if I can find something here. They changed this, it used to be easy. You know what? So sunspots. Let me try this. Current. Oops. Current. Maybe space weather. Yeah, there we go. Do we have a lot of sunspots? 2 little ones. Doesn't look really sunspotty. It's kind of cool, isn't it? Zoom into the acne of the sun. Let's try this. Sunspot activity versus time. Here's solar irradiance going like this. And it's floating around 1,361. Right around there. Sometimes it's more, sometimes it's less. And the temperature of the Earth varies, and then they throw this little, whoa, it's going way up. And that's because, you know, whatever. But the idea is temperatures do fluctuate. And right now we're in a minimum cycle. So our temperature should probably come down a little bit. And we probably will see that happen. Anyway, I just thought that was kind of a fun thing to see. Why are you not? Oh, here. Okay. Oh, by the way, what do we got? Oh, we got more tornado damage. Let's put the warnings out. It's a busy day, isn't it? Okay, so let's go back to this. Go ahead, Lena, would you read the next 2 paragraphs?
Yeah. A watt is a measurement of power or the amount of energy that something generates or uses over time. How much power is 1,360 watts?
Incandescent. That's like, you know, the light bulbs that if you touch them, they'd be hot. That's an incandescent light bulb.
Okay. An incandescent light bulb uses anywhere from 40 to 100 watts. A microwave uses about 1,000 watts. If for just 1 hour you could capture and reuse all the solar energy arriving over a single square meter at the top of the atmosphere directly facing the sun, an area no wider than an adult's outstretched arm span, you would have enough to run a refrigerator all day. The total solar irradiance is the maximum possible power that the sun can deliver to a planet at Earth's average distance from the sun. Basic geometry limits the actual solar energy intercepted by Earth. Only half the Earth is ever lit by the sun at one time, which halves the total solar irradiance.
Okay, now notice that the radiation is all pointing this direction. Do you agree that would be considered parallel beam radiation? I want you to imagine that I have a little area on the Earth. It's coming down. So the area is the area between the sunbeams. Okay, now let's go over here to the North Pole. Do you agree that the area coming down is still this wide, but it's being spread out over an area like this? Do you also see that that becomes a right triangle because the Earth is tilted? That flat surface is the hypotenuse. This is just a side. So the side of all these triangles is the same distance between the yellow arrows that are drawn. But the area that it's distributed over is the hypotenuse, the area over which the light is distributed. Do you agree that the area will get bigger and bigger the more tilted away from the sun we are? Why is this area, watch this, why is this area bigger than this area? What fact means that? Does that make sense to you? I mean, you have to tell me if you understand what I mean. Why is this area smaller than this area distributed over?
Isn't it just because of the spherical shape of the Earth?
Because the Earth is a sphere. If the Earth were a big cylinder rotating in space and the sun's over here, then all the radiation, no matter where I am on the cylinder, would be the same. But it's not. It's a sphere. Which means what? Which area gets the most intense radiation? Near the what?
Equator.
The area near the equator. There's a name for that area. What do we call the area of the planet that's near the equator?
Tropics? Is that?
The tropics. What do we call this area where we are at? And what do we call the area up here?
poles.
Or the polar, or right, the poles are the polar regions, right? Polar, mid-latitudes, tropics. We break the Earth into 30 degrees of latitude. 30 from equator to 30 is the tropics, 30 to 60 is the mid-latitudes, 60 to 90 are the poles, polar regions. So would you agree that the amount of energy hitting the poles will be less than the amount of energy hitting the tropics? So what I'm saying is that this area gets more energy. This gets less energy, which means the equator is hot, or it's warm. The poles are cold, which because of that gives us what? Gives us weather. So I've gone the opposite way. Pay attention, this is important. If I said, what's the ultimate cause of the weather? A second grader should understand what? The equator is warm, the poles are cold. That's a second grade answer. A more sophisticated answer is the sun's energy is more intense at the equatorial regions and less intense at the poles. The college answer is the sun has more insolation at the equatorial regions annually than the polar regions annually because the Earth is a sphere. The Earth, and here's what you need to know, the Earth is differentially, oops, heated by the sun because the Earth is a sphere. Now, there's another problem. First of all, does that make sense? That's why we have the weather. Okay, so you're nodding. I actually believe you. But do you understand that the Earth is also tilted on its axis? Would you agree that this is, what day of the year would this be when the sun's directly over the equator?
At the solstices?
No,
No, at the equinoxes.
at the equinox, right? EQU. This is the equinox. Oops, equinox. If the Earth were tilted this way, then where's the sun directly over? Is the sun directly over the equator? The answer is no, it's tilted 23.5 degrees. So where's the sun directly over? Of what?
Cancer.
Cancer. And then if it were tilted the other way, it'd be over the Tropic of Capricorn. So do you understand that the area on the Earth of highest insolation goes from the Tropic of Capricorn to the Tropic of Cancer and back and forth? So what does the tilt cause?
Is it seasons?
Tilt causes seasons. And it's all based upon insolation, and the maximum insolation changes. What are the two things that the tilt causes? What are the two things that the tilt of the Earth results in? Like, how does the tilt change the seasons? How does it change the insolation?
Earth's temperature changes.
Well, why? You're not wrong, Aaron, but why?
Because more. So when the Earth's tilted, one hemisphere receives more energy, and the other one less.
More what? It's more, what's the word?
Insulation.
Yeah. Isn't it more intense because it's more what? More direct. And what else does the tilt cause?
The day length.
Right? The length of day, which is really the length of daylight. Right? The days are longer when it's in the summer hemisphere. So remember, insolation base is based on two things, intensity and the duration. And both of those are changing as the sun goes over a different location. So we get these big variations in that annually do this. Where's my, and then I look at this graph. And this graph is explaining that. You see what I'm saying? It's like a flashlight, holding it off at an angle, it spreads out over a larger area. So look what I'm asking you to do, guys. I'm asking you to summarize what this diagram is explaining. And in order to summarize, what do you need to use? Words. In order to use words, you have to actually express your thoughts completely, not just a few words in a paragraph. That's what I'm looking for, to summarize. Now, do you understand what the answer is supposed to be? You just have to figure out how to express that. Now, what about this? Before I show you this, I want to show you something else. Twitter, Brandon Kopic. Listen to that roar. This is a violent tornado. Debris falling. Tornado on the ground right in front of me. Go up the mountain. Debris. Okay, he says it's a violent tornado. I'm not sure that he knows that. So hold on, I'm getting information while we're talking about it. Tornado emergency for Leeds, Alabama, Chelsea, Alabama, Indian Springs, Alabama, which is I think that's just east of Birmingham. Here, I want to see something cool. TV station. Hold on, let's get this one. WBMA Birmingham. Come on. Play this damn thing.
Introducing Chase First Banking, a debit card and application.
I'm about to die, but here's a commercial.
Teach them good money habits. Set account alerts, savings goals, allowances, and chores for your Chase mobile app. All with no monthly service fee. Chase First Banking.
Well, here we are a week after some tornadoes moved through parts of central Alabama. And
No,
again,
I don't
we are
want
looking
this.
at a severe-
I want live. There we go.
And it's going to be coming out into Calhoun.
Good. So we're tracking that circulation that is very close to Embry Bend.
Okay, so if I were to look at this place right here, and if I put a paddle wheel right in here, what would that paddle wheel do? If the winds are blowing this way and that way, a paddle wheel would start to spin.
Oh no.
This way. Now, because it's not super tight, that's what we call the mesocyclone.
There's major damage.
Ooh, look what it just did. Now, here's where the mesocyclone is. But here's where the tornado, it's a brand new tornado. That's intense. Yeah, that's 100 knots. So it just, that's gate to gate shear, Lena.
You said it was 100?
Yeah, let's see. Look down here at this, no, where is it?
Oh, it's gonna get worse.
Right there. What's the highest number you see? 40, 42? No, sorry, 46. What's the number, highest number you see? 49.5, 56.3.
Oh, wow.
And 39. So it's going this way at 39 knots and this way at 50. So that's a delta V of the difference is 89 knots, and that's gate to gate.
Oh no. Where Eagle Point, where is that?
I don't know.
Because there's major damage. In Eagle Point, I see a house that has been just collapsed on itself.
What are you looking at?
I'm talking to a bunch of friends.
No, what pictures are they showing?
Pictures on Twitter.
What's the person's name?
Here.
Just give me the name.
And here's another one.
It's hard to tell.
So
that's
that's looking EF2.
That's probably a 3.
It's unfortunate that.
Keep an eye on this, and we'll continue with our discussion. Does that make sense to you guys? Have you seen that kind of stuff before? I mean, I figure if we're talking about weather, we probably ought to talk about the weather a little bit. Here, just so you know, I'll show you something here. Here's later on this afternoon. Here's the sounding. Let me show you. This is the parcel. Let's do it this way. Here's the parcel. Let me make it larger. Remember, the parcel is always in blue. Here's the temperature in red. I really want you to think about this one here. So right there is your tropopause. It's also the EL. This whole area here is what? What is that, guys? That's all Cape. By the way, notice how fat the Cape is here? The Cape's around 1100. The convective inhibition's only 26. Here's your LCL, here's your LFC. So that's a little, it's not great, but it's possible this kind of a sounding can produce a tornado. And that's what that is. So that's what our soundings are enable us to do. If I look at what storms might be rotating.
Oh.
So there's supposed to be storms 3 to 4 o'clock starting to develop in Mississippi. And those are the big ones coming across. That's the NAM nest. Let's see the HER.
The HER is going to destroy it.
Doesn't do it nearly as much. Has one up here, big up into Georgia. This might be the one that's in place. This is pretty interesting, Sam. Look at the inconsistency of this model.
Right. Well, that's the HER for you. It's just it's consistent all the way up until right before the event.
That's the problem with models. You can't really use them. What's going on with that storm? Strong right there. But I don't see a debris signature really strongly. And that's it. Those are the only tornado warnings. Oh, I guess there's one way down here someplace. Let's see what this one looks like. Well, that's impressive. It's got rotation, but not nearly as much as this guy. So this storm has done some damage. Looks like it's about to do even more so. That's a pretty tight couplet.
That's very scary.
Not super. It's still too broad. It's just not tightened up, and I think that's the stretching. Well, there you go. That's cool. Okay, back to our studies here. So what we said, what is this graph telling us? What is this graph telling us? This is saying at This is the amount of insolation. What does insolation stand for? That's the incoming. That's the incoming solar radiation. So we talked about the top of the atmosphere. This is now at the surface. This is through the ground. And remember that some of the light doesn't get through if there's clouds, if there's scattering, if it's coming in and there's dust in the air, something like that, that's going to get rid of it. So this is how much is being received. So irradiance is emitted, right? Insolation is received. It's what's hitting an object. Remember, there's also the albedo, which is the percent reflected. The percent that's reflected. So we're not talking about that reflection yet. We're talking about what's actually hitting an object. So when I look at 90 degrees north, now I'm going to tell you something about this one. Notice it goes so high. Oops, goes so high. But then it drops to 0, which would make sense because after you get to the equinoxes, how long is the length of day? There is no day. So once you get to the equinox, there's no radiation coming in. So that tells me why I know the equator would be that way. What about this blue one? What's this blue line? When does it get, this one gets the most radiation in on those 2 days. So where must this be? Well, that must be in the equator because that's when the sun's most directly. When I go to the summer solstice, how far off of the horizon or how far off of the zenith is the sun when you're on the equator? On the summer solstice.
23.5.
23.5 degrees, right? Because it's over the Tropic of Cancer or the Tropic of Capricorn. So the equator, notice that the amount of radiation that's hitting the surface at the equator varies, but not by much. Like the minimum is around, well, I don't know, 380 watts per meter squared. The maximum is like, I don't know, 440. So it's only 60 watts per meter different. But there is some seasonal temperature change. Now, what if I go to 30 degrees north? In the winter, the least amount, it's around 240. And the most is around 480. So do you understand that at 30 degrees, there's going to be greater variability because of seasons? Now, here's the question. Which receives the most insolation on the summer solstice? Where on the earth gets the most? You should see the answer right there. Which one's getting the most? The North Pole. Can you believe that? On the summer solstice, the North Pole has the most amount of radiation. Now, obviously, it's not very intense because it's, on that day, the North Pole, it's going to be, this is 23.5 degrees. Off the zenith, it's going to be 90 minus 23.5 degrees, which is 66.5 degrees off the zenith. But what's the length of day at the North Pole?
24
What's the length?
hours.
It's 24 hours. So it's not that intense, but it's long. So the North Pole actually gets the greatest amount of insolation than anywhere else on the Earth on the summer solstice because it's sunlight for 24 hours. Actually, it's probably closer to the Arctic Circle, but whatever. But once I get to here, how much incoming radiation is there? And the answer is nothing. So when I look at the North Pole, it gets a little bit where it's a lot, but for the half the year, there's nothing. So what that says is this, and this is what our first question was many, many moons ago. I asked, this is good stuff. Oh man, this is, I don't know what book this is, but it's a good book. I asked you insolation versus latitude. And we get something like, wait, where was that diagram that we looked at from the beginning? What did I type in there? You remember that diagram? Well, I guess it looks sort of like this thing. Oops, where'd it go? This is not the biggest picture, but there it is. So we said that there is from around, let's say 40 degrees to the poles on an annual basis, there is more coming in than going out. But from 40 degrees to the pole, what does this deficit mean? More out than in. Right? So if that's the case, what should this area be doing? If there's more out than this, what should this area on the Earth be doing? Ryan?
So it means there's more energy going out than in.
Which would mean what?
Oh,
It's the Earth is losing energy there.
So it's doing what?
It's emitting energy.
Well, no. You're fine. But what does that mean? You said the Earth's losing energy there. So what does that mean?
I'm not sure.
Aaron? It's easy. It's an easy answer. There's more going out than coming in. What happens?
Cooling.
It gets colder. Right? If there's more going out than coming in, it gets colder. If it's getting more in than out, what does that mean?
Warmer.
It's getting warmer.
Oh, okay. So do you agree that we have part of the Earth trying to get warmer, and there's part of the Earth getting colder? But what does that mean? It means that when I look at the Earth, there's the Earth, and this is around 40 degrees latitude. The air that's warm here and cold there must be circulating. See, the air moves to create a balance, because according to this, there's an imbalance. So warm air goes to the north and cold air goes to the south. So the air circulates in order to try to create a balance. That circulation is the fluid motion of air, and that's called convection. You get a convective circulation. Make sense? Ooh, that's even worse.
Oh, I actually just took a direct hit.
Where's the TV guy?
County. And you can see the approximate arrival times on your screen.
On tracks for you. And remember,
Producing major damage in many counties, and it's probably been producing major damage in St. Clair County at this point. We'll know much more about that in a second, but it's across, this is moving northeast.
Ooh.
And again, Taylor, get farther away from the radar.
Okay. So let's go back. What do you think? Pretty interesting to watch the tornado?
Yeah.
Are you missing 11 to 15?
Yeah.
Which class did you like better?
I would probably say
Oops, your mic just went out. So I never got your answer. No, I can't hear you. Here, mute your mic and try it again.
okay,
Right.
I can hear you.
There you
Can
go.
hear me?
Yeah, I can hear you.
What did you ask?
Which class did you like better?
Probably 15.
Which class is harder?
I feel like they're both the same for me. I felt they're both hard.
They're hard in different ways, aren't they?
Exactly. Yes.
I just wish you were actually in class.
I
Wow,
know.
that's an impressive couplet right there.
Mhm.
Look at that. That's 92 knots outbound, 23 inbound. So big tornadoes going on today. Probably not sure if there are any EF4s yet. Anyway, so let's try to finish this little thing and then we can get out of here. So that's what that diagram talks about. And then we talked about this one, right? This question dealt with the fact that it takes the sun a time to sink through the sky. And then these pictures. So we should know the rest of this, right? This should make sense to you. Okay, so I need to go to the climate lab. Make sure you've done this. So Aaron, I didn't get the diagram correct.
You know, I forgot to attach it and
It's okay. I mean, I know that you did that, so.
yeah,
just-
it wouldn't let me send it again, so I
So
can email that to you.
basically what I want to say is this. Who needs a job? Raise your hand if you need a job. Oh, you're going to want this job. This is a good job. All right, Lena, I'm giving you the job. You're in the center. Okay. So what I'm going to do, I'm going to get a job and I'm going to tell you something that you can sell. I'm going to give you the right to sell something. So the day of the week, and then you're going to have your income and your outcome and your balance. Okay. So Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. You need to give me $50 a day to get the license. I am making $50 a day. That's your expenditure. Okay. On Monday, I start teaching you, and you're lucky you make one sale for 50 bucks. What's your balance?
0.
0. Okay, not a great. Tuesday, you're still new. You're getting a little bit better. You make 2 sales, 100 bucks. What's your balance?
50.
Wednesday, you're getting good. 150 bucks sales. What's your balance?
100.
Try again.
Oh, wait, what?
You made 100. You had 50. So your balance is 150. Right?
Oh, okay.
Now, Thursday, you're cranking. What's your balance?
300.
300 bucks. Friday, you decide you'll work, but you'll take the afternoon off. You make $100 worth of sales. What's your balance?
350.
Now, you don't want to work on the weekends because you're lazy, right? But somebody says, hey, call me back. And then they said, I'll buy it. What's my balance?
350.
And then Sunday, you take off. What's my balance? What's your balance?
300.
Okay. What day of the week was your best day of sales? What's your best day of the week, everybody?
Thursday.
Thursday. She made 200 bucks. But what day of the week did she have the highest balance? Friday and Saturday. Because what determines whether the balance goes up or down? What determines whether the balance goes up or down?
The income.
It's not just the income. Isn't it? Even though she made the most on Thursday, on Friday, she still made more than she lost. And her balance went up. Once we switch that, then the balance goes down. So what determines the balance is the income versus the outgo. You've got to look at both things. Now, the other day I asked you, what's the warmest day of the year? And we said it's mid-July, late July. What day of the year do we get the most incoming radiation? What day of the year do we get the most incoming radiation?
June 21st.
And why June 21st? Why is that the most?
Because that's the summer solstice and the sun is the most direct then.
Okay, and?
The longest days.
Right? Longest daylight. So good, Zach, right? What day of the year is the warmest? If June 21st is the best day, that's this, the warmest, what does that mean from June 21st to July 20th, let's say? What's happening on a daily average? More incoming than out. And the temperature goes up. Once we get to the end of July, what starts to happen? The outgoing is greater than the incoming, and the temperatures start to come back down. So what day of the year is going to be the coldest day?
Is it sometime after the winter solstice?
Yeah, sometime like mid-July. What's happening from the winter solstice to mid-July?
The balance just keeps going lower.
Because more
You get a lower income, I guess.
against a higher.
You're losing more heat than you gain.
Now, if I were to graph this up, that was a seasonal thing, right? That was a yearly thing. But what if I did this here? Here it's going to be SR. Here is SS. What's SR and SS? This is time. It's temperature. What do you think SR and SS is? You guys know the musical Fiddler on the Roof? Shannon, do you know that? So when do you think the most incoming radiation is?
Okay.
Right? The most incoming radiation is noon. When is the warmest time of the day, do you think?
3 o'clock.
Isn't it a little bit afternoon?
Yep. About 2 to 6 hours after noon. That's the warmest time of the day. When do you think the coldest time of the day is? The coldest time of the day is actually right after sunrise. Because even though we're getting radiation coming in, we're still losing more than we get for about 30 to 60 minutes. Then we start to warm up very rapidly. We're getting more incoming than radiation out. So the fact that the temperature goes up and down, this is known as the diurnal temperature variation. It's warmest 2 to 3 afternoon, 2 to 4, something like that, and it's coolest right after sunrise. And the temperature goes up and down. So here's the question for you. What would cause the temperature range to do this? Oops, that's actually. What could you tell me about the pink compared to the blue? The temperature variation is what?
It's less variation.
Less variation, less extreme perhaps, right? What would cause that? During the day. What causes the temperature not to get so warm during the day?
Clouds.
What? Clouds. What causes the temperature not to get too cold during the night? Clouds. But what do clouds do to the radiation coming in?
They reflect it.
During the day, they reflect solar. But what about at night?
They prevent the outgoing long wave radiation from getting through.
Why? What are they doing? What's different? It's kind of different. They absorb it. And then what do? Then they radiate it back. So the temperature can't get as cold on a cloudy night because clouds are absorbing and radiating energy. They don't get as warm during the day because clouds reflect during the day. So they reflect, it's shortwave radiation. They absorb and emit long-wave radiation. Does that make sense? Kind of different. So clouds are important that you understand that difference. So it's almost like a greenhouse. They don't reflect. That's not what they're doing at night. So when we look at our temperature variation, so watch this. Let's go here. Let's see what's going, storm, uh-oh, it's about to hit there. Yeah, it's looking nasty right there. No, right there. Let's go over here. So let's look at, oh, here's the new day one outlook. Let's look at this. Here's Illinois' page. Here's the temperature forecast for DuPage County. Notice the temperature is going up and down. But it didn't go down very much last night. It's not going up very much today. Why?
It's cloudy out.
Okay. Temperature's going to drop quite a bit tonight, then up, and then a little bit tomorrow. And then it's a big swing. So the big swings, like over here, it looks like a sunny day. So it looks like Monday and Tuesday are going to be sunny and warm. Temperatures in the 60s. You might get 60 degrees on Saturday, but then it gets really cold, back down to the 30s Saturday night. So it must be a cold front goes through, and then it only rebounds up to the mid upper 40s. Then it drops back down. Then it gets warm again on this. And then what happens next week? Gets cold again. So then on Wednesday, temperatures are still below 50. By the way, do we do our normal high? What's our normal high? So if you went to the page I told you to go to, you would have seen something like this. The climate statement for DuPage. Let's go ahead and do that. Normal high is 52. We went up to 57 yesterday, so it's warmer than normal. The normal low is 31 and it only got down to 45, so we're above normal. But if we have temperatures only in the 40s next week, that's below normal. And then we talk about the heating degree days. So yesterday, because it was 10 degrees above normal, there's negative 10 heating degree days. Because what is a heating degree day? All the degree days are based on what temperature?
65.
Based on 65. So if the average is 58, so that's the average is just the high plus the low divided by 2. If the average is 58, then I have to heat the air 7 heating degree days. Okay? Because if the temperature is averaging below 65, what are people going to use?
The furnace.
Use the furnace because it's going to be cold enough you'll kick on the furnace. If it's 65, you won't need anything. If it's warmer than 65, on average, what will it be? What will you want to use probably?
An air conditioner.
An air conditioner. So that's the way the power company has determined 65 to be that kind of, if it's averaging 65 degrees, people aren't using power very much. So if you look at your graphs or the numbers you had, when did we start getting into cooling degree days? What year, what day?
Around June 15th.
Okay, so it's not until June 15th where our average temperature is 65. And then we do that through what, September?
Yeah, September 1st.
Okay, so only June, July, half of June, July, and August, on average, do we have to use our air conditioners. Most of the time we're using our heater. And that's how that works. Now, the reality is, could you use your air conditioner earlier? Sure, because we get really hot days. And then what else affects our comfort level besides the temperature?
Humidity.
The humidity, right? The higher the dew point. So here, write this down. The higher the dew point, the less the variation of temperature. The higher the dew point, the less the variation of temperature.
Does that have to do with the water vapor absorbing?
Yeah, water vapor has a higher heat capacity, it's called.
Okay.
So it takes longer to warm up hot air. I mean, humid air.
Okay.
Okay, so dry air is going to go up and down. So if I have a day that looks like this, up and down, and then I look at another day that's very similar to, but it goes like this, what can that probably tell you if it's sunny in both places? The pink one's more humid, more water vapor. So let's ask this question. What kind of night gets coldest?
Well, first there would have to be no clouds.
Okay, so clear, right? No clouds. Because clouds are going to keep it warmer. So we need a clear night. You ever seen those big storm systems that start to clear up right in the evening time? Those are the worst because the clouds kept it from dropping too much or getting too warm, but at night it gets really cold. What else?
Would it be low humidity?
Or at least low dew point. Okay, what else?
Be like mid-January.
Well, obviously, I mean, longer nights, right? January's going to be longer nights. But what other things about the weather?
Does wind?
Okay, what about wind? Wind keeps temps warmer at night, mixes the atmosphere. But when it's windy and it's cold, it's, oops. Wind makes it feel colder. But the actual temperature will be not as cold if it's windy. It just feels bad. I personally would rather have common cold than windy and not so cold. One other thing though, and the answer is fresh snow. Because fresh snow, first of all, what does snow do?
Isn't it an insulator?
It reflects coming in, right, albedo, and insulates the ground. So the ground is warm, but it doesn't get out. The radiation doesn't get out. So the air gets cold on top of the layer of snow. So the air is cold. So we have a big snowstorm. It starts to clear up and it's windy. The next night, we tend to get really calm skies, high pressure, and that's when we get our cold. That's where our temperatures tank. Usually it's a day and a half after a big snowstorm because fresh snow has a high albedo and it insulates the ground, but it makes the air really cold. So there was a question. Oops, where is it? There was a question in the lab that says this. And I asked you, what did you think? Now, Isaac, you said you weren't so sure about this. Well, what do you think the answer to this one is?
Let me just reread this question real quick.
Did anybody answer it? I mean, you could be wrong. I don't care.
I answered, I don't think it's right. I just said because like in January, like we'll have the polar vortex, which will create like huge dramatic changes in their temperature. Whereas like in summer, it's like, I don't know, you get hotter days.
What you need to do is you need to look at this as going, okay, in January, it went from 67 to negative 20. That's 87. That's delta T of 87 degrees Fahrenheit on January. In June, it went from 99 to 50. That's only a delta T of 40 degrees. So those things about cold nights, what's the only thing different between January and June?
Snow.
Snow. If I have no snow, I can get warmer. If I have fresh snow, I can get colder. In June, I don't ever have snow. Snow never plays a role. Now, let's say that I could somehow make it snow in June. What would probably happen is that this number would go down. And now we're about 60 degrees. Now we're getting more realistic. So really, this is all about snow. The presence or the absence of snow. Last question, this one. And there's a couple of reasons for this. Obviously, in January, it's cold. W sub S relates to temperature. Remember we did this exponential relationship? So when it's cold, how much water vapor could even be in the air? Very little. So if it rained out, there wouldn't be that much. So on average, it's not very much. Besides, we might get snow, but snow doesn't have that much liquid equivalent. In the summertime, when it's warmer, I can get and therefore rain out a lot more. Besides, what kind of precipitation is more likely at this time of the year? What kind of precipitation? What's that symbol for?
Storms, thunderstorms.
So do you agree that a thunderstorm can really dump a lot of rain? So on average, you can go up really quickly. And in the wintertime, you don't get thunderstorms very often. So that's the answer to that. So you need to figure out a way to write that down. But those are the two questions you probably couldn't answer really well. The rest of them, you should be able to do it. And then we talk about what's an anomaly. What's the definition of an anomaly? It's a departure from normal. So I'm going to show you one last thing, and then we'll be done with class. Hold on a second. In this model, I'm going to show you temperature anomalies. So where it's red, it's warmer than normal by like 20, dark red is 20 degrees. So very warm, warmer than normal way up in Canada. Blue is colder than normal. These are the anomalies. So over the next few days, warm anomalies, warm, 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 and then, ooh, big warm anomaly. But then look what happens a little bit later. Now we start to get more cold anomalies. So that's next week where the temperatures are below normal, way down into Texas. And then we get above normal coming back later. So a lot of above normal temperatures here, but it'll go up and down for the next few weeks. And if you did, we did climate statistics, the standard anomaly or the standard deviation, this tells me how crazy it is. So kind of extreme warmth out here, but then the warmth is extreme a little bit, but it's fairly normal to have that much. Here's some pretty cold weather. So we're getting into some warmer conditions. If I wanted to see something like that, I can look sort of at an average. So 6 to 10 days. Colder than normal here and about normal, maybe a little bit warmer than normal. 8 to 14 days on the longer period, we're getting warmth into the plains. So this is really spring at this point. Now we're getting into April. Now we're really can be a little bit more comfortable with spring. I don't see any snow coming in. I don't think so. Oops. Let's see. No snow, maybe a little bit of snow up there, Madison. Warm air, oh. Maybe next Wednesday, this model brings in snow. How much snow does it bring in? An inch. So it might snow a little bit. But that, that's typical. We still get these cold fronts come in, a little bit of snow, but there's no big accumulating snow. So I don't see any more snow. And if we're going all the way to April now, chances are way, way less that we're going to get any snow. Okay, now, boys and girls, something kind of important, and that is you've got time to catch up. Everything needs to be turned in. You have a bunch of you need to turn in your class notes, which you haven't been doing that. Lena, Shannon, you've been doing your class notes. That's good, right? You're getting good points on that. I'm happy. The rest of you get everything turned in by the end of spring break. Now, you need to study so that you don't forget this stuff. I would say the beginning of today's lecture is a good thing to review. So go review some of the lectures. If I have a chance, I may put a little lecture review next week, and you can look at it next weekend. But there's no big projects due. Just catch up and get ahead, and then you'll be fine. Is anybody going anyplace for spring break? Lame. So then you won't be, just study and become an A student. What do you think, Isaac?
Yeah, I'm gonna be dog sitting for the whole week for my aunt.
Well, you have plenty of time to watch some old lectures. But don't forget, sometime after that, we have a little bit more to go through this unit, and then we go into unit 4, and that's more fun. But today was helpful, I think. I mean, I hope you understood the beginning part of this, so please do that. Sam, you know where our class notes are? If you go to, instead of this, if you go to forecast, you go down to the parent directory to forecasting, I'm going to put up today's discussion. I would like you to watch that, especially the last 15 minutes of it. That'll be up in about 10 minutes.
All right, sounds good. Thank you.
Okay, guys, have a wonderful spring break. And if you have any problems, just text or email me. I'll respond over the time.
Thank
Okay.
you.
Thank you. Have a good
Spring break.
break.
Have a good one.
Bye-bye.